Hello and welcome, everyone. That's right, we have a different screen today on this Frame It Friday, and that is because we're going to actually talk a little bit more about some math and some nerding stuff today. That is the goal, and that is what we're going to do. So, before we get started, who am I? My name is Sam. This is me. I'm happy. I went to school. I read some books. I studied a bunch of stuff. This is a book. You see this? This is art. This is my art skills. And I learned a bunch about engineering and spent a bunch of time designing houses. And so I'm going to give you guys some of that knowledge that I learned. And hopefully you can take it, use it, and get better at drawing and designing and all of that stuff. So we're going to use this whiteboard in front of us today. And we're going to do a super simple little house design. Look at a situation where we would have a beam. And then we're going to go over here to Forte Web. And I'm going to show you how to run through this software and do a simple beam design, so you understand a little bit about what's going on. We're going to keep it really simple. I'm not going to go into crazy tributary areas or anything, roof braces, any of that fancy stuff. We're going to keep it very simple and linear. And hopefully this is applicable and you guys can take some stuff from this. So let's get right into it. First things first, we are going to draw a house. All right, top down view of the house. Now, if this is our house and it's a rectangle, then this is what it would look like. Now, what we're going to do next is we're going to draw the roof planes like we would see on a roof plan. It would go around like this, and if this was a single gable on each end, we'd have a ridge running down the center of the house. All right, very good. Now, what we have here is, let's say that this width of the house is, well, let's call it 20 feet. So if that's 20 feet, then what we're probably going to want to do, and let's say this side is 12 feet, obviously not to scale. So we're going to have a beam that's crossing this way, and we want to use 2x6s. I'm using my mouse to do this. 24 inches on center as our ceiling joists and our rafters. And so to do that, what we got to know is our rafters can't span more than 11 feet horizontally without needing a support, and our ceiling joists can't go more than 14 feet horizontally without needing a support. So if we're going to run the ceiling joists and rafters left, right, then what we're going to need to do is we're going to need to get those in here. So let's do this and pick a different color here. I want the color. How do I use the color? Oh, it worked. Okay. So ceiling joists are going to be left to right. Oh boy. Like this. And the rafters are as well. Okay. So what we're going to think about is the beam. So let's actually put the beam in here. Let's use this nice pink color here. This is our beam. It's going to cross the wall like that. And our weight from the ridge is going to go straight down onto the beam with braces. And the ceiling is going to connect to this beam as well. And basically what we're going to do is load the center of this space onto this beam. Here's the dimensions we have. And we need to know what size this thing needs to be. Well, there are ways you could basically do what we call using tributary width. And basically what you, oh, I just need to move. I need to move the screen. Oh, there we go. So if we were going to use tributary width, we'd want to look at this thing. So we want to know how much weight is on the beam. What we're going to do is we're going to look at where the weight's coming from. Well, it's all coming from the ridge and it's all coming from the ceiling. So roof only first. If the ridge is right here and there's a wall right here, there's a wall right here. If I, I got to get rid of the pen. Hold on. If I go over here and do this example first, if we have a beam held up on each end and I put 100 pounds right in the middle, then how much do I have? How much weight is on each side of this beam? Well, if it's right in the middle, then the weight would be, presuming the beam was weightless. Well, let's say the beam itself weighed 100 pounds. Okay, so the beam weighs something and we're adding weight. So the total weight of this whole thing is 200 pounds. Well, this is right in the middle, and therefore, split evenly, we'd have 100 pounds of weight on each end of this thing. So what we're going to do is we're going to use that theory of the fact that half of the weight goes one way and half of the weight goes the other way. And we're going to apply that over here on this building. And what that's going to look like is basically this. Top down, I know that, take this pen back here. This is basically there's a whole bunch of weight over the beam right here, right? And so the ridge, let's think about the rafters. Okay, so there's our one rafter sits on the wall, and then it runs up, and then it sits on the ridge. So for one rafter, I want to know how much weight is contributing to the beam from that rafter. So halfway down the rafter, I would take all this weight and I would add it to the weight on my beam. And so what we do is we do that dimensionally without considering each individual rafter. We just do it as an average along a length. And so what we have here is from here to here, this width is called the tributary width. All right. And that is saying, hey, how much weight of this roof area is dedicated to this? And so we want to know the width of this because the length of our beam and like the way we're going to input numbers into the software matters. So what is the tributary width? It's this number. Now, if this is confusing, send something in the chat, leave a comment, that kind of thing. I can keep explaining this. This took me a long time to wrap my head around. What does this mean? But that is what we're going to do. So if that's what we got, that's the tributary width. We got to know that number. Well, what is that number? Well, this whole building is 20 feet wide. So halfway and halfway would mean that I've got basically 10 feet between here and here. This is 10 feet. Tributary width equals 10 feet. It's a big equal sign. Okay, and then what's my unsupported length? Well, let's round up and assume that this is exactly 12 feet across. So this is the unsupported length of the beam. So if we were to go over here and draw this beam, it looks like this. It's got a wall on one side, a wall on the other side, and it's got this even load of the roof and ceiling on top of it, evenly dispersed across the thing, effectively evenly dispersed. We don't care about small spacing. And this width in between the walls is approximately 12 feet. So how do we figure out this guy? We are going to use software to figure out this dude, is what we're going to do. So here's the situation. We'll reference this if we need to, but here's what we're going to do. We're going to go over here. We're going to take a look. So first thing you got to see is in the first floor, I have the ceiling beam. Now I created a new object and I said, hey, I want it to be this ceiling beam dude right here. So I did that guy. Now it's in the floor system. It's drop beam. This is like positioning, kind of matters, kind of doesn't. You can type in some notes, yada, yada, yada. And what you basically need to know is we're going to not care much about the member info. At the very end of this, it's going to compare some of our criteria to this. And so we could use like, hey, what's minimum to code? Or like what's really good, like good stiffness stuff. And you'll find a lot of times that when you design a beam, you're actually designing it to stiffness standards. You're not designing it to actual failure of the beam itself. Because our wood will bend a lot more before it breaks. And so that's what we're going to do. So we'll leave it as code minimum because that's fine. And then you can check some other things that, you know, are for complicated designs, but we're not going to leave that alone. So spans and supports. First thing, let's show our beam. Okay, so the blue area is showing the loading area, and this is our beam. It's got a wall on each end. And we're going to say the span between each of these was 12 feet. And before you know it, look at that. That's updated to 12. So it's 12 feet wall to wall. Perfect. Now let's look at each side of the beam. So the side one here, support one, bearing length is 3.5 inches. What does that mean? Why is it 3.5 inches? Well, it's 3.5 inches because this is a wall, and we're assuming it's a 2x4 wall. 2x4 walls are made out of 2x4 lumber, which is 3.5 inches wide. So it's saying, hey, the beam is sitting on 3.5 inches along the beam's length on side one and side two. See that? So if you had a thicker wall, you'd put a different number in here, or a thinner wall, you put a different number in here. And I will explain why this number matters at the end. Basically what happens is we don't want to actually crush the wood. If we have too much weight in a small enough area, we can actually crush wood due to compression. Most of the time that's not a problem, but it can happen. So dimension, location, clear span, yeah, whatever, it's fine. Excuse me. So bottom flush mounting. Okay, so this is like, how is the beam attached? Is it a top mount hanger? Like, see this? See how it moved? Is it top mount hanger? Is it a face mount hanger where there's another beam and it's got a face mount? See that? It's changing how this beam is supported. And it's doing that because at the end it'll say like, oh, well, what hanger do you want to use here? And it's got a whole bunch of cool things the software can do. But we're going to go back and say bottom because it's just sitting on something. And then it's going to say, hey, what's it sitting on? Because now it looks different than this side. Well, what is it sitting on? A beam, a ledger, a plate, a pocket, a stud wall. What's it sitting on, right? There's all this stuff. Well, I'm going to sit on a stud wall because I just have a regular old framed house here, nothing fancy. So we're using that. And then what material is the wall made of? Well, this material matters because all these materials have different densities, which gives them different compressive strengths. So we're going to leave, if I was in Texas, I'd probably say Southern Pine because that's what most stuff is going to get framed out of. If you're going to use cheap Home Depot wood, you're probably going to use SPF because that's a much thinner, lighter wood and less dense, not thinner. And it has a less compressive strength. So we could leave it as that if we wanted to be safe. And then it's going to ask, hey, what's the accessory to this? Is this beam just sitting on top of the wall or is it blocked out? See how this side has a dashed line on the end of the beam and this side does not? Well, let's go back to the drawing. If we were to look at this beam and give it a cross section, that would look something, like this, right? If you took this and sliced it, the way we look at it that way is going to be like this. We have a beam. We draw an X because it's a cross section. There's a wall it's sitting on. And what we don't want to happen is that we don't want the beam to tilt and rock left, or sorry, that's right or left, okay? We don't want it to tilt or rock over. And you'd be like, well, why would it rock over? Why would it tilt? And the answer is because beams aren't always loaded. Beams aren't always like loaded straight down. For example, if there was a roof plane above this like this, and I had a roof brace coming down like this, then what's happening is I'm actually introducing an angular side load to this beam. And so there's a portion of the load that is going this direction and a portion of that load going straight down. So this is the part that goes straight down and loads the beam that we don't have to worry about. And this part is actually trying to turn our beam over. It's trying to flip the beam over. And that's not good. We don't want that. So to fix that and resolve that so we don't have that problem, we block the ends of the beam and we keep them from rotating. So if you ever go up an attic, you'll usually see something where they've taken some 2x4s or something and they've put them up like this at an angle and they've nailed them in on both sides of this, something like that. There's all kinds of ways to do this. You could use full blocking or whatever, but basically you restrain the top of the beam so that it can't rotate. So if we go to here and we look at this, we'd say, well, it's either blocking or none. And blocking implies that the end is restrained from rotating. So great, it's blocked. We don't want it to rotate. And that's safe to assume in most cases that you should do that. Okay, so now down here, the bracing interval. So basically the same thing applies like this, but all the way down the length of the beam. So right now we're only concerned with the ends with the first part, but the second part is saying, hey, oh, hold on, fix that. The second part is saying, come on, screen. How far, like all this part in the middle, can this part in the middle rotate? And you'd be like, well, why would the part in the middle rotate? Well, either it's the same thing and the side load is on top of the beam, or here's another thing that happens. When you put a bunch of weight on top of a beam, the first way it actually fails is the top of the beam will try to bow. So if we look top down on this scenario, it would look something like this. We have a wall and we have a wall over here and the beam goes straight across. Everything's nice and happy. And if you load this beam super duper heavy, the first way it's going to fail is actually going to be by bowing. And it would do something like this. The top of the beam is going to deflect and fail in a column sense. And the reason for that has to do with how beams respond to stress. So if you load a beam like this, what's really happening is we give the beam a cross section. Actually, let's do this. So if we were to slice, here's the wall. This is like this view right here. If that's the wall and I have the beam going like this, and I slice it and I make a little break, and I look at the inside of the beam right here, what's actually happening is the inside of the beam is doing different things. The top of the beam is in compression, and the bottom of the beam is in tension. And in the middle of the beam, there is no compression or tension. And so basically, when you load a beam like this, the bottom of the beam is trying to rip itself apart, and the top of the beam is getting smushed together. And there's a little thing that happens when you smush stuff under compressive load. If you ever imagine a ruler, if you take a ruler, it's nice and thin and tall, and here's your desk, and you take your ruler and you stand it up. If you were to put your hand, here's a hand, that's a hand. If you put your hand on the ruler and imagine yourself like touching and balancing the ruler, it's great. When you're balancing it and barely touching it, it's nice and stiff. But if you were to push down really hard on the ruler, what would it do? Well, it's not going to stay straight up. What it's going to do is it's going to go boo, it's going to bow like that. That's called a buckling failure. The material can't, like, it can handle the compressive weight of what you're putting it on, but the shape of the material and the length and the slenderness makes it so that it can't take that and it bows out. Okay. So the same thing happens with the top of the beam because it's being squished. The top of the beam bows out like this. Therefore, if we block the whole beam with these side angular things or some other way and restrain it from rotating left or right down the whole length of the beam, then we actually can make the beam stronger. That's why this matters, okay? That was all to explain why this matters. So this is saying, hey, the top edge of the beam, is it braced? And the bottom edge of the beam, is it braced? Well, the bottom edge of the beam is going to be flush with our ceiling. So what you got to think about is that all the way along this, we've got ceiling joists that are either joist hangered in or something. They're connected to the bottom of the beam. So all the way down, if our spacing is 24 inches on center, then we're good. The other thing that's happening is you're going to put sheetrock on the bottom of that beam too. And if you're going to screw off the sheetrock 7 inches on center with screws, that's going to add strength as well. But we typically don't try to consider drywall strength when we're doing this. So we're going to pretend that it's not there. That's conservative. So the bottom edge is going to be custom and every 2 feet. And why 2 feet? Because our ceiling joists were 2 feet on center. So the ceiling joists are adding stiffness to the bottom edge of this beam so it doesn't bow, which it wouldn't do because it's in tension. But the top edge is probably just floating. So I would say end supports only, most likely, because you're probably not going to brace the top. Now, if you had a really big one, you can use these as tricks to save yourself some strength and stuff. But yeah, that is the situation we got going on. So that's how we consider the supports of the beam. So we're good. Now, how are we loading the beam? We're almost done, I promise. You take care of the spans and supports, you take care of the loads, and you just pick one out, and then you're good to go. Okay, so what are the loads? All right, here's how we define a load. What is the type of the load? Is it a point load or a uniform load or a tapered load? Like if the load is changing along the length of the beam, like there's more ways to load things. Let's say uniform. It's going to be consistent, even load across the beam because that's what we're dealing with here. Now, where would you have a point load? If you had a whole bunch of roof braces coming into one spot, that is a point load because all the weight is coming into one place. Most of the time, though, it's spread out. So this is where that tributary width comes in. Because I'm going to say uniform pounds per square foot, full length of the beam. What is the tributary width of my load? Well, again, we said 10 feet wide all the way down the roof is loading the beam. So I'm going to say 10 feet. And the placement is on top of the beam. Well, so in this case, the ceiling joists are on the side, but the roof is on the top. So in this case, top is fine. This is not super important. Okay, now dead load is something we got to consider. When we're looking at a load like this, there's 2 loads going on. First, we're going to deal with the roof. We're going to call this roof only. Okay, so the roof dead load is 10 pounds per square foot dead, 20 pounds per square foot live, if we're just keeping it simple. What does dead and live mean? Dead load means the weight of the structure itself is adding weight, and live load means material, or not material, but like equipment or people walking onto the roof is going to cause a loading scenario. And that kind of like comes and goes. So there's factors associated with that. So 10, and remember up here, this says uniform, and it says my units are going to be in pounds per square foot. So 10 pounds per square foot is my dead load. My roof slope, let's say it was a 612 roof because I designed it. And now see this, it's going to adjust the dead load because the roof is pitched and I gave it 10-foot tributary width in a plan view. And there's actually more weight than that. So if we had a super steep roof, we have more roof across the same like plan view width. Hopefully that makes sense. So the steeper this pitch gets, the higher this factor gets because it's adjusting for that pitch for us. So we'll leave it at a 6 because that's fine. All right, floor live load. There's no floor load. We're on a roof, so that's 0. The roof live load is 20 pounds per square foot. So 10 and 20, easy to remember. This is a roof load. We're good to go here. If you live in a snow area, you would use the snow load if it's higher than the roof load. So that's fine. And we'll leave that alone. Now, we'll go ahead, copy this over. Okay, now what we got going on here is that we're doing the ceiling load now, the ceiling and attic. So the ceiling is the same thing, okay? Half of the ceiling is on the beam, the other half is on the walls. So 10-foot tributary width. We're gonna load, I guess, well, if we wanna be super specific and we're gonna hang on this, let's do this. We'll say front side of the beam. It doesn't matter which side you pick. And then what I'm gonna do is I'm gonna split it up. I'm gonna make 2 loads for this. So half of the ceiling weight's hanging on the front side of the beam. Dead load for ceiling with no storage is gonna be 5 pounds per square foot dead load, 10 pounds per square foot live load, and there's no pitch. So it's exactly 5. And this is not roof live load. This is gonna be ceiling or floor live load, okay? So this is 1/2 of the side. So I just did like this side is the 5 foot, and I'll do the other side 5 foot. But to be more correct, I'll just take this, copy it, change this to backside, and now I have the combined 10 feet of ceiling, the total 10 feet of roof. All my loads are good. Everything is correct. This is as correct as it can be. So we'll go here to skip. If you're going to put holes in it, you can do it here. You can either do other stuff here. We can ignore that most of the time. Now we're going to pick the product. Okay. So for a job like this, I'm going to assume that commodity lumber would be just fine. So regular lumber, you can use Doug fir, hem fir, southern pine, spruce pine fir, different species here. Most of the time, your big lumber is going to be southern pine, at least where I'm building. So 2x southern pine, and I'm probably going to get grade number 2. Unless I specifically ask for number 1, most of my stuff is going to be number 2. So I'm going to check that. And then I'm going to go ahead and use, they all have all the way up to 2x14 in here. So it's either 2x4, 2x6, 2x8, 2x10, or 2x12. And let's just guess, because this is a guess and check game. Okay, so I'm spanning 12 feet. I'm spanning 12 feet and I'm holding 10 feet of roof and ceiling is how I would say this. And so what I'm going to do is I'm going to guess. I'm going to say, let's say 2 2x10s. Maybe 2 2x12s. Let's check that. We click on solutions and we check. And it says failed. All right, 219%. So we have failed twice. This is much too much weight for this particular beam. So we'll go back to product selection and we'll say how many plies? Well, let's add another ply. So now there's 3 2x12s, glued and screwed and nailed and all that stuff. How are we doing? Well, now we're down to 124 right here. So we're doing better. It's getting stronger. Let's keep going. So we got 4 2x4s. Four 2x12s. Now how are we doing? Okay, we passed. We're 87%. We usually don't like to push this number over 90% because that's asking for problems. And that's pretty happy. And let's look at our deflections because we want to check, are we going to break? And what are we deflecting? Those are the main factors. So let's check it out. Actual at location. So total load, which means if you put all of the live load and all of the dead load on the beam at the same time, you will get this deflection at 6 feet 3.5 inches in. So if I go back to here, remember the beam was spanning 12 feet. So it's saying, believe it or not, beams deflect the most in the center where they are the weakest. And so in the center, if you load it with all of the loads from the house design that we just did here for super simple sake, and we use 4 2x12s, and we go back and check the math, it says our beam will deflect 0.2 inches. All right, that's pretty darn straight. The 2x12s themselves probably are not even toleranced to being 0.2 inches straight. So there's, that's probably pretty darn good, okay? And that's total load. So you could think about it this way. Here's the live load, which means that if you only have live load, that's what it is. If you have the total load, here's what it is. So if you would think about, well, if I never put a live load on it, then it will be the difference between these two. But yeah, so 4 2x12s works. If you are wanting LVLs because you want to make a nice, perfectly straight beam, then what you would do is you'd go back to product and say, well, I don't want commodity lumber. I'm going to use an LVL. So I'd check LVL, that's the thickness. And I would easily say that the 11 1/4 or 11 7/8, 2 plies of it would be totally fine because this material is very strong. So 4 2x12s or 2 LVLs, and this is even stronger. See that 67%? And look at this. It's actually less likely to break, but it deflects more. See that? This is 0.26, the other one was 0.2. So you can bounce back and forth, choose different materials. If you wanted the glue lam because you couldn't get LVL, you would select glue lam. I'd pick a 3.5. I'd say just 11 7/8. Let's try that. And look at that, even stronger. Look at that, 40%. 40%. And this is like basically the same dimensions. So you can use different materials to do the different same, things. Okay, so this is 0.229. We're good here. Now, what are the other pieces? Well, this is shear. You're basically never going to fail this unless you've got like crazy beam design stuff going on. So you can pretty much ignore this. And then member reaction. This is the important part. So remember back here in spans and supports, I said, hey, the beam sits on 3.5 inches of wall. Watch what happens if I say the beam sits on only a 1/2 inch of wall on both sides. And we go back. See that? It's only sitting on a 1/2 inch. And we go back here. Look what happens. So our member reaction has failed. And what this means is that there's so much weight on the end of the beam, which it's claiming, if we go to the report, it says, here's the totals. Okay, so the dead load, floor load, and roof live load, and the total factored load is 2,400 pounds. Okay, so we built a house that's 20 feet by 12 feet. We put a 12-foot beam right in the middle, and the weight on each end of that beam is 2,400 pounds. Okay, so don't stick your finger underneath there. That is not going to feel good. So like here's just this this is where these numbers come from, right? So if you put 2,400 pounds on a 1/2 inch by 3.5 inch area, I say 3.5 inches because this beam is 3.5 inches wide. Okay, that's the area for compression that you have. It crushes the wood. Like there's not enough wood there. It's going to squish. It's going to crush your wall or crush your beam, and that's why the support area matters. So check this out. Check this out. If we have a 3.5 inch beam or a regular 2x4 wall, here's a perfect case. We are fine. See that? We're 48% capacity. This is saying that we are allowed to put, and this is based on 3 things. We selected the species of the wall. We're going to make the wall out of spruce pine fir. The wall is going to be 3.5 inches wide, and our beam is 3.5 inches wide. So that has an area, and there's a strength pressure associated with that area, which gives us this number. We can put 5,206 pounds on spruce pine fir with a square of 3.5 by 3.5. That's what that means. And our weight, our calculated factored weight is this. So we are good by 48%. We're fine. Now check this out. If you design big houses and big beams, most of the time, guess what happens? If we take this tributary width up to like 15 feet, and let's say jump the span, like now we're crossing a garage, 20 feet span, right? Does our beam work anymore? Definitely not. Look at this. Look at it. We're failing like crazy. Okay. So if we take a glue lam, a 5.5, well, let's try 3.5 glue lam, and we make it taller, we're still failing. We make it 24 inches, as tall as possible. Okay, here's what I wanted to say. The beam passed. It's not going to break. The deflection's good, 0.28 inches. That's totally fine. And here's the other cool part is for glue lam beams, they're actually cambered. So they're actually bowed offset in the direction of what you're like trying to load them. So when you load them, they straighten out, which is really cool. And that's just because of the manufacturing process. So that's a neat thing to know, but we're good. The beam actually is not going to fail. What's going to fail is the wall at the beam. And that's because we could only put this much weight on the end of the wall, but because of the way we're loading the beam, there's actually this much weight on the beam. So it's too much. So what do? Well, you either use what you got to do is you have to increase the contact patch between the beam and the wall because you just got to spread the load over more area is what you have to do. And so there, or you pick a wall. Let's try this. So if we go back to this and we say, yeah, don't use spruce pine fir, use southern pine. That's a little more dense. Let's put southern pine walls in. Let's check the solution. Hey, look at that. Southern pine is much more dense, so we're fine. Now we can take about almost 7,000 pounds. So we're good. Now, if we go back to this, I mean, there's lots of ways to solve this. It just depends on what you're going to be doing. This is why you don't buy Home Depot wood, friends, because it's made of this whitewood stuff. Okay, so if we're failing, the other way to do this is change the beam and make the beam wider. So here's if I just make it wider and I leave it at 24 inches, we are now 27%. And this thing's barely deflecting at all. It's like 1/10 of an inch. Okay, so this is a way over designed beam. But we also fixed the problem here. So we can actually go back, made the beam got wider, and we can actually make it less deep. And now let's see. Okay, now here's a common trade-off that people like to do with glue lambs. Because it's wider and less deep, it's going to be more bendy. All right, so our load is still good, but look at this deflection. Now we're going to actually design limiting this number, because now total load is, 0.6. That's almost a 1/2 inch. Okay, and the dead load is basically 1/4 of an inch. Now over 20 feet, a glue limb is normally cambered by about 1/4 inch in 24 feet. So we're gonna, when we set dead load on top of this and build the structure, it's gonna level itself out. And then over time with total load, it's gonna deflect 1/4 of an inch. So we don't actually want to go less than 16 inches here, because we would bend too much. And we're not going to break, because that's just not the limiting factor. And we have, we increased the width of our contact patch. So we've got plenty of weight, or we got plenty of capacity for weight. And that's that. You could print out the report and say, well, look at all this math that figured out all this good stuff for us. But yeah, just put some spans and supports in, put some loads in, understand where your loads are coming from and how they're attaching, pick out something that works. And that is how you know what beam is good. And this is all free software. Anybody can use ForteWeb if you know how to poke your way around in here. So that is the special class that we are doing for this Frame It Friday. I hope you guys learned something. Quick chat shout out, because we got chat shout outs. Look at this, Green Observer. Hello, everyone. Welcome, Green Observer. Glad you are here. Glad you have decided to come learn. It's good to have you. And you make great music, so shout out to him, because we're about to take us out with some music by the one and only Green Observer. Thank you guys for coming on. Hope you learned something. I will see you in the next one.
That's the code.